This video is about orbital hybridization. By the end of this video, you should understand why orbital hybridization is necessary, understand how hybrid orbitals form, and be able to predict orbital hybridization based on molecular geometry. Before we consider orbital hybridization, let's consider how covalent bonds form using atomic orbitals. If we take Lewis structures and the atomic orbital theory, we can put them together to give us the valence bond theory. This theory assumes that bonding electrons exist in between atoms. In other words, bonds occur when an atomic orbital of one atom overlaps with an atomic orbital of another, thereby bonding. This is seen in the picture at the right. This allows electrons making up the bond to share the space between the two nuclei. Here you see in this H2 molecule the overlap of the two 1s orbitals. The electrons in the bond then exist between the two nuclei of the hydrogen atoms. In the HCl molecule, we have hydrogen's 1s orbital overlapping with chlorine's 3p orbital, and again the electrons exist in the space between the two nuclei. Likewise for chlorine, which has the overlap of two 3p orbitals. Here's a quick refresher of orbital shapes. We'll mostly be looking at s and p, so quickly remind yourself of the shapes of the s and p orbitals. Let's consider the case of methane to help us understand why hybridization is necessary. Methane has a tetrahedral structure with carbon as its central atom. The electron configuration of carbon is shown here. Carbon then has one available s orbital and three available p orbitals for bonding. However, this creates a problem. Experimental data tells us that all four of the CH bonds in methane are completely identical. So how is it possible to form four identical bonds if you're using two different types of orbitals? The orbital overlap with an s orbital would be different than the orbital overlap with p orbitals. So we need to account for these four equivalent bonds using two different types of orbitals. Looking at this example in more detail, here we see the orbital diagram for carbon. Again, we see a problem in that it looks like there's only two unpaired electrons available for bonding. Orbital overlap generally occurs when we have an unpaired electron. According to our hybridization theory, in order to form four equivalent CH bonds, which we know it does from our experimental data, carbon will need to promote an s electron to a p orbital and form hybrid orbitals. Looking again at the orbital diagram, notice that one of the two s electrons will be promoted to the 2p orbital. This now gives us four unpaired electrons, which means we can form four bonds. However, it still doesn't account for the fact that all of those bonds are identical because we have two different types of orbitals, s and p. So the theory tells us then that the s and the p orbitals essentially merge to form four hybrid equivalent orbitals. We call these orbitals sp3 orbitals. Note that sp3 indicates that it's made of one s and three p orbitals. Hybrid orbitals then have a combination of properties of the orbitals that make them up. There'll be a combination of shapes and a combination of energies of the atomic orbitals that formed them. We'll look at three types of hybrid orbitals in this unit: sp, sp2, and sp3. Our methane example looked at sp3 hybridization. Let's revisit this before moving on. sp3 hybridization, as we said, is formed from 1s and 3p orbitals. This will occur whenever an atom requires four equivalent tetrahedral orbitals. So anytime we see a tetrahedral geometry or a variation on tetrahedral geometry, we know that we have sp3 hybridization. The energy of the sp3 orbital is between that of the s and the p level. Likewise, the shape is between that of s and p. Here we have the spherical 1s and the bow tie shaped 3p. When they merge, we end up with an orbital that looks kind of like an exclamation point. Recall again that these orbitals are simply areas of probability in space. So these are essentially solutions to a math problem. These aren't physical entities. Now you can see how these four sp3 orbitals can come together around the carbon to give us four equivalent areas for orbital overlap. Again, as we said, the energy of the sp3 orbitals will be between that of the original s and p. You'll notice that these ones are closer to p since they're made up of 3p and only one s. Looking at the final piece of the puzzle here, let's see how this allows for orbital overlap. The overlap of the sp3 orbital from carbon and the 1s orbital from hydrogen will form a single bond. These are often called sigma bonds because they're end-to-end overlaps of atomic orbitals. So here we see our carbon with its 4 equivalent sp3 orbitals available for bonding. Each hydrogen has a 1s orbital, and here we see the overlap between an sp3 and an s, another sp3 and an s, and another and another. This gives us 4 equivalent bonds and is consistent with our experimental data. Note that sp3 hybridization also occurs in trigonal pyramidal molecules because these still have a base tetrahedral geometry. Again, we see 4 equivalent sp3 orbitals, but in this case only 3 of them overlap to form sigma bonds. The 4th contains the pair of non-bonding electrons we see on the nitrogen in the Lewis structure. Looking now at sp2 hybridization, this is formed from 1s and 2p orbitals. This will occur whenever an atom requires 3 equivalent trigonal planar orbitals. An atom is surrounded by 3 bonds. Note one might be a multiple bond, a double or a triple bond. It's important to note here that this will leave one p orbital unchanged. Looking at a picture, here's our spherical 1s and our bow tie-shaped p's. When we put them together, they form this sort of mushroom-shaped area of probability, and this gives us 3 equivalent sp2 orbitals. Looking again at the orbital diagram involved here, we see an electron gets promoted from the 2s orbital, and then we form 3 hybrid orbitals. Note here that once these 3 equivalent sp2 hybrid orbitals form, we have an unchanged 2p orbital. This will become important later when we look at how multiple bonds form. Turning now to sp hybridization, sp hybrid orbitals are formed from 1s and 1p orbital. This occurs whenever an atom requires 2 equivalent linear orbitals, and this will leave 2 p orbitals unchanged. Here we see our s and our p, and our hybrid is a combination of both. Looking now at our central atom, we have 2 equivalent sp hybrid orbitals around the central atom. Again, we see that a 2s electron is promoted to the 2p level, but when our hybrids form, we have 2 unchanged 2p orbitals. Again, this will become important with multiple bonding. Consider the BeF2 molecule, which is a linear molecule with beryllium as the central atom. Here we see that beryllium has 2 hybrid sp orbitals, each overlapping with a 2p orbital of fluorine to form 2 BeF bonds. Notice the beryllium will also have 2 unaltered 2p orbitals. In this case, they're not in use. We'll see in the next video when we do use those unaltered p orbitals. Here's a table summarizing what we just looked at. Note that you can always predict the orbital hybridization based on the geometrical arrangement around the central atom. That brings us to the end of this video. Let's review our goals. First, we looked at why orbital hybridization is necessary to account for equivalent bonds from unequivalent orbitals. Then we looked at how hybrid orbitals form. And finally, we learned to predict orbital hybridization based on molecular geometry.